For years, the story in AI has been pretty simple. Bigger is better. To get smarter AI, you need bigger computers, more data, bigger everything. But what if that whole idea is wrong? A new paper from the experts at NVIDIA just dropped, and it's turning that whole idea on its head. They're making a bold claim. For most of the things we actually use AI for, small isn't just an option, it's the future. And today, we're going to dig into why. So this image perfectly captures the shift we're talking about. On the left, that's the old way. We thought AI needed these giant, power-guzzling data centers. We're talking entire buildings just to run one system. It's all about brute force. But now, look to the right. The new way, the idea we're exploring, says that all the power you really need might just fit onto a single, super-efficient chip. It's a huge change, moving from a sledgehammer to a scalpel. And it changes, well, everything. And this really is the million-dollar question, isn't it? For the longest time, if you asked anyone in tech this, the answer was a quick and confident, of course. Bigger models, more power, that was the only way forward. But this NVIDIA paper hits the brakes. It asks a really important question. Have we been so focused on building the biggest possible brain that we've totally forgotten to ask what we actually need it to do? Their answer is pretty surprising, and it could shake up the whole industry. Okay, so here's our game plan. First, we're going to bust that bigger is better myth and see just how expensive it's gotten. Then, we'll meet the hero of our story, the small models. We'll look at the actual proof of how they can run circles around the giants. We'll also be real about the challenges they still face. And finally, we'll peek into the future, which isn't really big or small, but a really smart mix of both. Let's jump in. All right, first things first. Let's talk about the giant in the room, or, well, in the data center. For what feels like forever, the AI world has been in this massive arms race. The driving philosophy was simple. If you want smarter AI, you have to make it bigger. Period. And the scale of this race has been absolutely mind-blowing. Just look at this timeline. It shows you how crazy fast this has all happened. Now, parameters, you can just think of those as the little knobs inside an AI's brain that it twists to learn things. Back in 2018, GPT-2 seemed huge with 1.5 billion of them. 2 years later, GPT-3 jumps to 175 billion. That is a 100 times leap. And now, with models like GPT-4, we're talking over 1 trillion parameters. It's just exponential growth. It makes you stop and ask, is this even necessary? And here is the big reality check from the paper. These mega models can do amazing things, right? They can write poetry, debate philosophy, you name it. But what are businesses actually using them for every day? Well, it's this stuff. Simple, focused, and honestly kind of boring tasks. Pulling an address from a PDF. Figuring out if a customer email is about a billing problem. They're basically using a super genius to do simple data entry. This quote from the paper just nails it. It's so simple and so perfect. Why are we using a sledgehammer to crack a nut? It's like we've built this incredibly powerful tool that can smash through concrete walls, and we're using it to open a peanut. And as we're about to see, using a sledgehammer for a delicate job isn't just overkill. It's unbelievably expensive. Which brings us to the bottom line. The cost. Because using that AI sledgehammer isn't some abstract problem. For companies all over the world, it's a huge number on their monthly bills. It's very real, and it's very, very expensive. So check this out. This chart shows you the cost difference for one single, simple task. That big bar on the left, that's our sledgehammer, the big, expensive model. The little bar on the right, that's a small, specialized model, our little nutcracker. And the difference is just insane. For a ton of those everyday business tasks, the big model costs 100 times more to do the same job. And get this, you're paying 100 times the price for the exact same result. Sometimes the result is even worse. To make this even more real, the paper gives this incredible example. One company, just one, could save over $50,000 a month, not a year, every single month, just by swapping out their big, clunky AI for the right tool for the job. Now imagine that kind of savings across thousands of companies. We are talking about a massive economic shift here. Okay, so if the big models are the pricey sledgehammers, what's the alternative? It's time to meet our hero, the small language model, or SLM. This is our nutcracker, the smart, efficient, specialized tool that's actually built for the job at hand. So what is an SLM? Basically, it's an AI model with under 10 billion of those parameters or learning knobs. Now, that might sound small, but here's the secret sauce. They're fine-tuned. Think of it like this. A giant model is like a person who's read the first page of every book in the library. They know a tiny bit about everything.
An SLM is like a brain surgeon who spent 20 years studying one thing. It's a world-class expert in its one specific job. And in that one job, it's absolutely unbeatable.
NVIDIA's whole argument for these small models is just beautiful in its simplicity. It really comes down to three things. 1, they are more than powerful enough for most jobs. 2, they're just better to work with, they're faster and more reliable. And 3, the one that makes every CFO's ears perk up, they are so much cheaper. It's a win on every front. Okay, so that's the theory. But talk is cheap, right? Let's look at the actual evidence. Because the NVIDIA researchers didn't just guess about this, they put it to the test. And they found that it's not just about being cheaper. In a lot of cases, these small models are just plain better. This right here. This table is probably the biggest shock in the entire paper. Take a look. On top, you've got Phi 2, a little model with just 2.7 billion parameters. Underneath, you have Llama 2, a much bigger model at 13 billion. Now, common sense would tell you the 13 billion parameter model wins, no contest. But the data says the exact opposite. The little guy, Phi 2, actually outperforms the bigger one on important tests. How is that possible? It's all about the training. The small model was trained on super high-quality, specialized data. It proves it's not the size that matters, it's the quality of the education.
And that amazing performance leads directly to incredible savings. This chart shows you what happens in the real world. That huge purple chunk, that's an 80% cost savings for companies that switch to using small models first. And here is the absolute best part. They saved all that money with zero drop in performance. The exact same results for a fraction of the price.
One of the data engineers in the study really summed it up perfectly. They said SLMs are lightweight, faster to train, cheaper to run, and often just plain more effective for specific jobs. It's the whole story in one sentence. It's not about brute force. It's about being smart and efficient. Okay, but let's be real for a second. This isn't some magic wand that fixes everything. The researchers are really clear that small models are not the perfect answer for every single problem. So let's take an honest look at some of the hurdles that are still in the way.
The paper points out 4 main challenges. First, that fine-tuning, turning a model into a brain surgeon, takes really good data and people who know what they're doing. Second, these are specialists. If you want an AI to have a deep, creative conversation, a small model is just the wrong tool for the job. Third is just inertia. The industry spent years building for giant models. Switching gears takes time and new tools. And finally, you've got the marketing bias. We've been told bigger is better for so long that it's actually a challenge to change people's minds.
So, where does this all lead? What's the end game? Well, it's not about small models wiping out the big ones. The real future is a clever combination of both. The paper has a technical name for it, but I like to think of it as the Lego approach. You don't build a castle with one giant block. You use a whole bunch of different, specialized pieces that all fit together perfectly.
Here's how this Lego system works. It's actually pretty brilliant. First, a task comes into the system. But instead of going straight to a big model, it hits a smart router, which is actually a tiny little SLM itself. Its only job is to look at the task and ask a simple question. Is this easy and routine? If the answer is yes, boom, it gets sent to a fast, cheap, specialized small model. But if the router sees the task is new, complex, or creative, then and only then does it call in the big guns, the expensive, powerful model. It's basically an intelligent traffic cop for AI tasks.
And this isn't some far-off dream. It's already happening. Customer service is using this to answer 90% of questions instantly and cheaply. Businesses are saving millions. But maybe the coolest part is what it means for you and me. This efficiency means we can have powerful AI that runs right on our phones without needing to connect to the internet. Imagine a truly private personal assistant right in your pocket. That's what this makes possible.
This leads us to maybe my favorite quote from the paper, because it really flips the script on the whole conversation we've been having about AI. We hear all this talk about big models replacing humans, but what's really happening on the ground right now is that small models are starting to replace the big models. The revolution is here. It just looks a little different than we thought it would.
So in the end, the future isn't a battle between big and small. It's about building smarter systems that use the best of both. But after seeing just how powerful and efficient these small models can be for the stuff we do every single day, it really makes you think, doesn't it? So I'll leave you with this question. After seeing all this, are you leaning more towards team small models, or are you still on team big models? Thanks so much for watching.